Throughout history, especially pre-scientific history, catastrophism has always been a more popular notion as an explanation for how the world has evolved than slow, gradual evolution. Many religious accounts are replete with sudden and/or catastrophic events that change the world, from the creation myths prominent in all sorts of religious traditions, to Noah's flood, to the predicted rapture. Indeed, it was not until the middle of the 19th century that our modern view of gradual evolution came to dominate our discussion. The geological processes of volcanism and plate tectonics that shape the Earth, and the biological processes of mutation and natural selection that shape the species, are very slow processes, evolving and unfolding over millions of years. Nonetheless, catastrophes retain a strong emotional appeal. We like dramatic events. And now we know that they sometimes do occur on Earth, wreaking change on a planetary scale. In 1979, it had long been known that the disappearance of the dinosaur fossils occurred relatively abruptly, about 60-some million years ago, where abruptly, in geological terms, means in less than a few million years, which is about as well as one can date the layers of fossils laid down in rock. In geological eras, this is known as the Cretaceous-Tertiary boundary, or, for the German spelling of Cretaceous with a K, the KT boundary for short. It marks a distinct change between fossils below this level, longer ago into the past, and fossils above this level. Indeed, it appears that this marks one of the points of a very large number of extinctions occurring at a specific point in the history of the Earth. Walter Alvarez, in 1979, was a young geologist at Berkeley, and he was looking for an accurate clock to measure the rate of ocean sedimentation for this particular period of time, hoping to find a clue as to why both land and ocean species underwent such an abrupt change at this time. Indeed, by looking at all of the fossil record, it appeared that more than 50% of all species on the Earth, plants, animals, ocean creatures, went extinct at the same time the dinosaurs did. It wasn't just big creatures, it was the tiny little forams in the ocean. Species of those went extinct at the same time. Indeed, some records suggest that up to 95% of these ocean-dwelling species on the low end of the food chain went extinct about this period. Alvarez chose the element iridium as his clock. Iridium is number 77 in the periodic table, and its atomic mass is number 193. Indeed, it's one of the most massive non-radioactive elements. It's called a noble metal in analogy with the noble gases. Argon, helium, krypton don't form any molecular bonds at all because of the complete shells of electrons in their outermost orbit. The noble metals aren't quite that way, but they are also very reluctant to form compounds with other things. Platinum is the most common of the noble metals, and iridium is a rare one that he thought would be useful as a clock. The bulk of iridium settled to the core of the Earth during its formation. Just like when you pour oil and vinegar together to make salad dressing, you see the oil, which is less dense, float to the top, and the vinegar settle to the bottom. Likewise, the mix of elements that made up the Earth, which is not representative of the mix of elements in the universe as a whole, nonetheless have also separated such that the elements on the surface of the Earth are very different from the elements inside. It's instructive to actually take a look at the elemental composition of the Sun and the crust of the Earth and compare the two. The Sun is composed 98% of hydrogen and helium gas. The next most common element is oxygen, and it makes up slightly less than 1% of the Sun. The Sun is representative of the composition of the universe. Most of the universe is hydrogen and helium, and all the other elements are just traces. The Earth, as I mentioned earlier, lost most of its hydrogen and helium very early in its phase. Helium is extremely rare on Earth today and is only there as a consequence of radioactive decay, whereas the hydrogen has escaped completely except for that that's combined with oxygen and made water and various other chemicals on the surface of the Earth. The Earth's surface composition is in fact dominated by oxygen. 46.7% of the Earth's surface is the atom oxygen. 27% is silicon. Silicon dioxide is sand. And the next most abundant element is aluminum, which makes up 8% of the crust of the Earth, with 5% in iron, 3.5% in calcium, and 2% in a number of other elements like sodium, magnesium, and potassium. So these elements are greatly overrepresented on the crust of the Earth. However, they do not represent the bulk composition of the Earth. This is obvious if one just looks at the density of the Earth as a whole versus the density of its surface rocks. If you take the entire volume of the Earth, which is easy to measure, and the mass of the Earth, which we know from its orbit around the Sun, we get that the Earth has an average density, that is mass divided by volume, of 5.25 grams per cubic centimeter. And if you pick up a bunch of rocks on the surface and you put them on a scale and you measure their volume, you find that surface rocks have an average density that ranges between 2.5 and a little more than 3 grams per cubic centimeter. Well, if the whole Earth is about twice that dense, it's clear that the core of the Earth must be much denser than the rocks on the surface. This was the first clue that sedimentation, separation of the heavy elements from the light elements, had occurred. Today we know that the core of the Earth is largely iron, about 79% iron, 7% perhaps silicon, 5% nickel, and lots of other trace amounts of these heavy elements which have settled out when the Earth was still in a molten state towards the core of the Earth. Thus, elements like platinum and iridium, gold, and silver are very rare on the surface of the Earth. And Alvarez thought that iridium might be a nice way to measure the sedimentation rates at the KT boundary. Why? Because most of the iridium on the surface of the Earth comes from interplanetary space, riding in with the roughly 40,000 tons of space dust that settles onto the Earth each year. This dust has its origin in the origin of the solar system. Most of the material of the solar system in its early days was gathered up into the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. But there's little bits left over that have never managed to make it onto the surfaces of large planets. In particular, there's a large belt of rocks ranging in size from a couple hundred kilometers down to size you can hold in your hand, called the asteroid belt, between the orbits of Mars and Jupiter. There's millions of these rocks, and they're constantly colliding with each other and producing dust. The Earth travels around the Sun each year through this cloud of dust, and it gradually settles onto the Earth. Now, 40,000 tons may sound like an enormous amount of space debris coming in every year, but if you calculate how much that means in a layer spread over the Earth, it's only about a couple billionths of a centimeter per year, and over the entire 4.5 billion years of Earth's history, if that sedimentation rate were constant, it would only add up to a layer about this thick. So we're not about to get inundated by this dust. Nonetheless, it carries to Earth in the form of tiny particles ranging in size from about 1/100th of a millimeter, far too small to see, up to about a millimeter in size, grains of sand which actually burn up as they go through the atmosphere and produce what we call shooting stars, although their atoms still settle to the Earth. It carries to Earth a representative sample of the material of the solar system, undifferentiated like on Earth. Thus, it contains the element iridium. Now, it's important to note that iridium-193 is not radioactive. The clock in Alvarez's scheme comes not from the fact that the atom is going to decay, but from the fact that this infall rate of dust is very constant. So, when the ocean sedimentation rate becomes high, the concentration of iridium will be low. A lot of material, gunk from the surface of the ocean settling to the floor, will have come in over a short period of time, and the amount of iridium that's come in that time is small. Vice versa, when the sedimentation rate is very low, a small amount accumulating every year or decade or millennium, the amount of iridium accumulating that time stays constant, and the iridium concentration will be higher. What Alvarez found in a layer of sediment in Gubbio, Italy, that was now raised above the sea, was that the iridium concentration jumped from 0.3 of a part per billion to 7 parts per billion, by a factor of 25 precisely at the KT boundary, above which no dinosaur bones are found. Now, there's two possibilities for this huge sudden change. Either there was a huge sudden change in the sedimentation rate, or there was an extra influx of iridium from space. He then went to a deposit in Denmark, where the same level was exposed above the sea, and another one in New Zealand, and found that there, again, the iridium layer right at the KT boundary jumped by a factor of as much as 130 from below the boundary to at the boundary. In 1980, this led him to publish a paper entitled Extraterrestrial Cause for the Cretaceous Tertiary Extinction. It was published in Science, and I suspect that the only reason it was published in Science was because in addition to his two co-authors who had done the geological fieldwork and the laboratory analysis with him, he included his father, Luis Alvarez, who is a Nobel laureate in physics. The paper proposed that a meteor impact had killed the dinosaurs. Catastrophism was back, and most scientists simply didn't believe it. I remember distinctly a lecture in 428 Pupin, the room in which I lecture and the room in which Robbie introduced the atomic clock, where Luis Alvarez gave a talk on this paper in the spring of 1981. He made a fascinating, to me, case for the impact of a large object, 10 kilometers in size, which, among other things, spread iridium dust over the entire Earth. I remember walking out of that lecture with people shaking their heads, saying, just don't believe it. Well, 30 years later, Alvarez was unquestionably right. The evidence for a meteor impact and its global consequences are overwhelming. In fact, late in 2008, just a couple of months ago, I attended another dinner at Columbia honoring Alvarez for his discovery, in which the citation went on at some length about how he had reintroduced the notion of catastrophes into legitimate modern science. The iridium layer has now been found at the KT boundary at over 120 different sites around the world, with a distribution of concentrations that steadily decreases as you go away from the Caribbean Ocean, suggesting that that's where the meteor landed. Indeed, the crater made by the impact has now been found. As a consequence of oil exploration in Mexico, it was discovered that on the tip of the Yucatan Peninsula, there is a large region below the surface, now filled in by sediment, of fractured rock that extends down for several miles. This is now called the Chicxulub crater, after a word in the local Mayan language, and is, as Alvarez had predicted, roughly 200 kilometers in diameter, implying an asteroid of about 10 kilometers in size, hitting with an energy that's roughly 50 times that of the world's entire arsenal of 10,000 megaton nuclear warheads. It was a big bang. The rock was vaporized to a depth of 2 kilometers. 900 kilometers, 500 miles away in Haiti, the ejecta, the material that rained down from this impact, is about half a meter thick. In addition to being rich in iridium, the ejecta layers also contain very unusual things: fused quartz, little hard spheres called tektites, things that are glasses, like glass, diamonds, and zircons. All of these things only form under extreme pressures. Diamonds are normally made miles down in the earth with a huge overlying burden. In this case, they were made instantaneously as this huge rock hurtled towards Earth at 40 kilometers per second and smashed into Mexico. Zircons, it turns out, are particularly valuable for dating this event. In fact, you can use them to date events ranging from tens of millions of years ago to billions of years ago. Zircons are made up of the element zirconium, which is atom number 40 in the periodic table, 1 atom of zirconium, 1 atom of silicon, and 4 atoms of oxygen. And they form beautiful little crystals. They're valuable for dating because in the formation of the crystal, the element lead is specifically excluded, while the element uranium is readily substituted for some of the zirconium positions in the crystal lattice. As a consequence, one can monitor the decay of uranium to lead. The method is particularly accurate because there are 2 different isotopes of uranium that are involved. Uranium-238, the most abundant element, the isotope, which makes up 99.3% of all uranium found on Earth today, and uranium-235, which makes up most of the remaining 0.7%. The difference in the abundance of these two isotopes is clear by their half-lives. Uranium-238 has a half-life of 4.5 billion years, just equal to the age of the Earth, so since the Earth's formation, just half of what was originally present has decayed away. Whereas uranium-235 has a half-life that's 7 times shorter, only about 700 million years, and thus, as one would expect, 7 half-lives have gone by, and so 1/2 to the 7th power, or only about 1% as much, is left behind. Now, uranium-238 decays to lead-206 through a complicated series of almost a dozen steps. And uranium-235 decays to the isotope lead-207. Thus, in a single crystal, one has 2 different independent radioactive clocks. Given their precisely measured half-lives, we can predict at any point in time what the ratio of uranium to lead for each of these 2 isotopes should be. And we can plot that on a curve where the ratio of uranium-235 to lead-207 on one axis and the ratio uranium-238 to lead-206 on the other axis. We then can plot, by measuring in different points in the crystal the amount of lead and uranium remaining, what the ratio is. Now, if we assume there's no lead in the original zircon, a safe assumption given how it's formed, and that all of the lead present comes from uranium, we could instantly get a date. But it's possible that some of the lead atoms produced in the decay of uranium have been leached out of the rock by various geological processes. Nonetheless, lead-207 and lead-206, being chemically identical, will have been leached out at just the same rate. And so by plotting the ratios of uranium to lead for each of the 2 isotope sequences, we get a perfectly straight line on this same diagram. Where that straight line intersects the theoretical curve of predicted half-lives will give us the age of the sample. These ages are accurate to better than 1/100th of 1%. Using a technique called SHRIMP, which stands for Sensitive High-Resolution Ion Probe, scientists love cute acronyms, we can peel away the layers of the zircon crystal bit by bit and see how over time if it's been altered by geological processes. Nonetheless, this clever diagram of the theoretical curve versus the measured quantities of uranium and lead provides us an age precisely. The answer in the case of the zircons produced in the meteor impact that ended the reign of the dinosaurs is 64.5 million years, with an accuracy much better than 1/10 of 1%. Direct evidence has also been found that allows us to reconstruct the immediate aftermath of the impact of this huge meteor with Mexico. Layers of sandstone created in a Caribbean-wide tsunami have been found from Alabama to Guatemala. It's a very special kind of sandstone because unlike the normal kind, which is built up over hundreds of thousands or millions of years as layer upon layer of sand accumulates, there are no little channels through this sandstone which correspond to tunnels that little worms make as they wiggle through the floor of the ocean. This huge layer was laid down suddenly by a tsunami and solidified without the chance for biological disturbance. In addition, we find a layer of soot all over the world from the massive forest fires that were ignited by the impact. The impact made such a shock wave, a sonic boom, if you will, in the atmosphere that propagated over the entire Earth and was sufficiently potent to instantly ignite all of the lush foliage on Earth into enormous wildfires. The ashes from those fires are everywhere. Now, it turns out the dinosaurs were extremely unlucky as to where this meteor, which totally by chance, happened to hit in Mexico. The rock in Yucatan is rich in anhydrite, a gypsum-like rock. Gypsum is made of calcium, an atom of calcium, atom of sulfur, and 4 atoms of oxygen, calcium sulfate. This rich sulfur mix, when vaporized by the impact and thrown into the atmosphere mixed with water vapor, becomes H2SO4, sulfuric acid. Now, it turns out when sulfuric acid is thrown high into the atmosphere, as it is today sometimes by volcanoes, the Mount Pinatubo eruption in the early 1990s being the most recent example of this, it condenses into tiny little droplets which are extremely reflective of sunlight. It makes a reflecting blanket over the entire atmosphere of the Earth. Sunlight, instead of coming in and warming the Earth, just bounces away, reflecting back into space. And temperatures on Earth apparently plunged from about 20 degrees Celsius, a sort of comfortable 70 degrees, to minus 5 degrees Celsius, below freezing, in a matter of a week. We even know the month in which this meteor hit because of this sudden freeze. A geologist working in the fossil beds of Wyoming discovered the fossil of a lily pad leaf from this period of time. Now, you know what the back of a leaf looks like. It looks like the branches of a tree, a central vein and smooth branches coming off it. These are the little conduits of water and substance in and out of the leaf. Well, in this particular fossil, rather than the smooth flow of these lines, the geologist found a very jagged, fractured kind of look. And he was very confused as to what kind of plant would leave such a peculiar angular structure to its leaf vein system. Until he had an idea. He took a lily pad that was alive today and stuck it in his freezer overnight. When he took it out, he found the same angular breaks in the system of veins on the back of the leaf that he saw in this fossil. And, judging from pollen that was encapsulated at the time in the reproductive state of that leaf that he found in the fossil, he could tell that it was sometime in June, 64.5 million years ago, that the dinosaurs died. In addition to the sulfuric acid thrown into the atmosphere, it doesn't stay up there forever, and it eventually falls out as acid rain. We're not talking about acid rain such as that produced by power plants today, which has caused the introduction of some of our pollution control laws. We're talking about lots of acid rain, pure sulfuric acid in the amount of about 10 kilograms for every square meter of soil. Now, how, you might ask, could we possibly know the amount of acid produced in the atmosphere? Well, we can estimate it from the size of the crater and the amount of sulfur that we think was there. But we have another record, a remarkable isotopic record left in the skeletons of the little forams in the top of the sea. The ratio of strontium-87 to strontium-86, as I've told you before, is a critical one for dating and tracing the isotopic signatures. And strontium and calcium are homologs, and so strontium is easily incorporated into the shells of these creatures. The strontium-87 to strontium-86 ratio in the ocean being a very big place, is pretty stable. And it goes along at a steady level for a long period of time, right up until the KT boundary, at which point there's a sudden jump in the strontium-87 to strontium-86 ratio. What could cause this? Acid rain. It turns out the strontium-87 to strontium-86 ratio of rocks on land, the continental rocks, is slightly higher than that of the strontium-87 to strontium-86 that's dissolved in seawater. But this deluge of sulfuric acid pouring out of the sky after the meteor event actually eroded the rocks on land sufficiently, which, running into the rivers and out into the sea, changed the strontium-86 to strontium-87 ratio of the entire ocean, sufficient to have it reflected in the foram shells that we see in ocean cores today. Quite remarkable. Longer-term impacts came from alteration of the atmospheric composition. After the 100 trillion tons or so of dust and acid rain fell out of the atmosphere, probably over a few years, sunlight could reach the surface again. The huge amount of water vapor that was thrown up by the explosion, it landed in part in the Caribbean Sea after all, in addition to the huge amount of carbon dioxide released when the limestone in the area was vaporized, and the huge carbon dioxide released from the forest fires, which raged all over the earth, caused an enhanced amount of CO2 in the atmosphere. And extra CO2 in the atmosphere leads to extra heat-blocking powers of the atmosphere, meaning the temperature rose. The greenhouse effect raised temperatures for about 10,000 years. We'll talk more about the greenhouse effect in a few lectures. There's excellent fossil evidence of massive changes in life at the KT boundary. There was a massive die-off of plants. About 57% of all species seem to have gone extinct. Immediately thereafter, there was a blossoming of fungi. Why? Because fungi don't need photosynthesis, so they can thrive in the dark, as you know, feeding off the decaying matter from all the plants that died when the sun went away. This was followed by a huge increase of ferns. an effect that we've seen recently in the eruption of Mount St. Helens. The eruption of Mount St. Helens, the volcano in Oregon and Washington, flattened all of the material and killed all plant life on the sides of the mountain. The first species to be reintroduced are ferns. And we see this in the fossil record from the spores these ferns left behind right above the KT boundary. The species of amphibians and birds largely appear to have survived this, but the big winner was the mammals. Mammals came into existence before the KT boundary, and they started diversifying about 30 million years before this catastrophic event. By the time of the KT boundary, however, most mammals were really pretty small, sort of rat-sized creatures. But because of their small furry nature, and perhaps their ability to store up nuts for the winter, they survived this terrible asteroid-induced winter, unlike the massive dinosaurs who needed to eat huge amounts of plant life every day. When all their plants died, they went with them. As the dinosaurs disappeared, ecological niches opened up for the mammals to thrive. And though their extreme diversification, which we see on Earth today, didn't happen for several million years, the opportunity was there, and mammals now dominate the Earth. About 6 million years ago, an early line emerged from the hominid family from the great apes, chimps and bonobos, our closest relatives. Using molecular clocks, we can date this event, consistent with the fossil record in which the ages are determined from radioactive dating of the associated rocks. Many species emerged and evolved from this family. Homo erectus about 1 million years ago, and Homo neanderthalis about 400,000 years ago. But both of these species lost out after the emergence of Homo sapiens, us, about 150,000 years ago. And here we are, 150,000 years later, only 0.003% of Earth's life, piecing that history together again, atom by atom. The Cretaceous Tertiary meteor, the KT meteor, clearly had a global impact on climate for many millennia after the event, and it profoundly changed the balance of life on Earth. It was, however, neither the first such impact, nor was it the only time that a mass extinction had wiped out a large fraction of all species on Earth. Indeed, an event of unknown origin killed more than 90% of all species on land and in the ocean about 251 million years ago. Whether this was caused by an asteroid or not, we don't know. The surface of our Earth is constantly changing because of the erosion of wind and water and because of the wandering of the continents, earthquakes and volcanoes, the effects of plate tectonics. So that meteor crater may be lost forever. There are at least 3 other mass extinctions that have occurred over the last 500 million years since life diversified in the Cambrian explosion. And actually, a 4th is now underway. The extinction rate today of all species of plants and animals and ocean-dwelling creatures is estimated to be at least 100 times the average rate over the last 500 million years. And of course, we know who's responsible for this latest mass extinction. So the history of life has been a bumpy ride. Next time, we'll trace that history from the interstellar clouds where the molecules of life collected to us.